Hello, my name is Helena Garcia Escudero. I'm a graduate student at the University of California, Irvine, and it's a great pleasure for me to share my research in this online conference and hopefully have some very interesting discussions on the next upcoming weeks. So in this talk, I will share my previous and current work as my near future research interest that is focused on cosmology and its relation with cosmological tensions. So let me begin with or getting everyone a brief introduction on the Standard Cosmological Model, or lambda CDM, which is a mathematical model of the Big Bang theory, which is based on three major features. The first one is inflation, which predicts a flat universe with almost scale invariant density perturbations and gravitational waves. The second key component is cold dark matter, or slowly moving dark particles that, together with the inflationary density perturbations, lead to a very detailed picture of structure formation. And finally, the cosmological constants, that's also known as lambda, which is associated with that dark energy. This model is consistent with enormous high-quality observational data from our universe from different epochs. And as an example, I'm showing how well the model, in this case represented by the red line, fits the observational data, which are the blue points. So this is a plot from the CMB anisotropy data. So this model provides a great precision to what we know or what we have observed from the universe until today. And we can test the consequences of the model, and this is what it's leading cosmology from the 1980s until today. In addition to this, another important thing of the model is that it can be characterized by 6 parameters, which made it somehow a simplified way to describe our very complex universe history. So, okay, lambda CDM, it's great, but it's true that there's a few significant statistical tensions that arise within this model. One of them is the Hubble tension, or H0 tension, which is a mismatch between the present expansion rate of the universe, that's what we call H0. So the tension arises from 2 ways of calculating this constant. One of them is using the distance ladder that is built by Cepheid variables and type 1a supernovae, and that value of the expansion rate of the universe today derived from the angular spectrum of the cosmic microwave background given by the Friedman lambda CDM cosmology evolution until today. So one of the questions that I asked myself was how, from a subjective point of view, since I have not developed any of the models that I studied in my work that you can check on the reference that I'm putting on the slide, how well beyond or propose beyond the standard model extensions do on solving this cosmological tension. So how did I answer the question? So first of all, I consider 3 baseline datasets that corresponds to different epochs of the universe and have small statistical errors and a large amount of data, which corresponds to the Planck CMB data in 2018. So the BAO from the Sloan Digital Sky Survey, DR16 datasets, and finally the Pantheon sample that the data released from 2018. So I used these 3 baseline datasets, and I added the Gaussian likelihood of the Hubble constant. That's the most recent result from the Schues team from December 2021. So these are the final results of a chi-square test and a calculation of a statistical called the Ikaki information criteria, which is a statistical that measures the goodness of the fit, but it penalizes models that are more complex. So as I mentioned, Lambda CDM has only 6 parameters, and some of these beyond standard models extensions are more complex. So these models are penalized by this criterion. And then, so what we did was doing this chi-square test on Lambda CDM and then on each of the models, and adding the different data sets. So the red bars correspond just adding the CMB data, green bars is CMB, BA, and BAO, and the blue lines would correspond to the 3 data sets and the Schuh's likelihoods. And once we calculated the delta AICs for each of the models, we found out that there were 4 winners. How did we choose the winners? So we checked the results from the AICs with respect of the Jeffreys scale, which is a statistical scale that says that if the AICs are more negative, meaning more negative that the model is doing better than the baseline model that you are assuming, they have a strong preference with respect to the baseline model. So our winners are in this order: early dark energy, WCDM, primordial magnetic fields, and N-effective. I'm in this slide, I'm also showing what's the preferred value, for example, for N-effective, which is 3.48. This number will appear later on the presentation. And this is the result of running MC-MC chains on these beyond standard model extensions. And as well as calculating the delta AICs, we also checked what was the remaining tension. The H0 tension today, it's around the 4-5 sigma level with respect of Lambda CDM. So, we calculated here 4.63. So our winner, early dark energy, would reduce this tension up to the level of below 2 sigma. And on the right-hand side of this slide, I'm showing a plot with the central values of the expansion rate of the universe with all of these models. An additional question that we asked in this work was seeing how these models do when we added another tension that arises with Lambda CDM, which is the S8 tension. As you can see on the right-hand side of the slide, there's a lot of values that can be inferred from low redshift probes, which are much smaller than the value of the S8 or sigma 8 constant, which is a cosmological constant that measures the amplitude or rate of growth of structure in our universe. So there's another mismatch between the high value of this parameter when you consider Lambda CDM and use CMB observations with respect to the lower value obtained by low redshift probes. So we added to our analysis this S8 prior, and a question that may arise is why did we choose this particular prior? So it's important to highlight that the S8 tension is not as stringent as the H0 tension, so we decided to choose a value of the sigma 8 parameter from this low redshift probe, in particular from X-ray cluster, that makes the tension stringent. So in case that this tension it does exist, and how well or bad would these beyond standard model extensions do in solving H0 and S8 tensions together. So the results are that none of the 4 winners of our H0 analysis go beyond this strong threshold, but the winners are the same as the ones we obtained when we just consider the H0 tension. So these are the main results from our work. No models are above this strong threshold, but it's true that the S8 tension might not be a concerning tension anymore, but that's a matter of debate that hopefully we can have in the next few days. So the final conclusion from these works is there a model better than Lambda CDM? So the answer that I concluded with this analysis is that none of the models studied in this in this research do significantly better than lambda CDM when solving both tensions simultaneously. And the models that do good on solving H0 tension are the ones that do also good on solving both of them. So we have the same order and the same winners, although none of them goes above this strong threshold. It's true that all of these four models give a negative AIC, this meaning that a negative AIC is that the beyond standard model extensions achieve a better fit with respect of lambda CDM. So I would be interested in having more detail on this question in the next discussion sections. Now let me move on to another neutrino physics topics, and I want to bring your attention on this Planck 2018 plot that they presented on the paper that I'm referencing on the bottom of the slide, which highlights or which shows that the Planck prefers some of the neutrino masses, which is negative, which is, as we all know, a not physical result. So I'm trying to answer the question of where is this stringency from Planck 2018 results coming from? And if this, with my analysis, I want to again test different data sets and see if cosmology prefers a massless neutrino, which is in conflict with the neutrino oscillation observations that we have that claim or that have proven that neutrinos do have mass. So this is something that it needs further exploration. And I plan to update some of the neutrino masses constraints and see if cosmology prefers or shows the existence of any additional EV-scale neutrino states. I'm planning to use the most updated datasets, which are Planck 2018-2020, as well as the ACT and SPT CMB observations, and adding some new supernova datasets such as DES Year 5, Union 3, or Pantheon Plus. One of my guesses from this is from these results is that the Planck 2018 polarization data might have some physics hidden behind that we should test, and as well as seeing how the tau, the lambda CDM parameter, can affect these negative or massless neutrino cases. So I also leave some room for discussion in the next few days. And the final topic that I want to cover, it's related to the thermal history of our universe, the expansion of the expansion history and thermal physical process that happened in the early universe before Big Bang nucleosynthesis remain relatively unconstrained by observations. And the predominant model for the early universe postulate it underwent inflation. And when this period comes to an end, all of the particles that are kinematically permitted are directly generated through the thermal bath that inflation decay produces. The heating temperature of the universe refers to the temperature of the universe after inflation. The particles transfer their energy into standard model thermalized particle, establishing this initial hot and dense state. The radiation domination evolution leading into the required era of BBN places the lower limit on this reheating temperature, which it says to be right now of 1.8 MeV. So on the bottom of the slide of one of the works that highlighted this in 2018, Graciela Gelmini et al., and they show how low reheating temperature universes reduce the scattering epoch, with results on alleviating these cosmological constraints. But it's true that on the keV high mixing angle parameter space, we still have a lot of constraints coming from X-ray observation, cosmology, galaxy formation. But I was motivated or challenged by some laboratory experiments that are exploring or will explore this parameter space in the near future, such as KTRIN Tristan is the detector that's being implemented right now, Hunter or Magneto-Nu. So the question is, what might happen in cosmology if these experiments do detect a signal in this part of the parameter space? So we came up with this idea that, and you can check it on the link that I'm putting on this slide, that I show that a new sterile neutrino with RR decay to radiation through a C prime boson or a new scalar are largely unconstrained by cosmology if you consider a low reheating temperature universes. So on this slide, I'm showing two low reheating temperature scenarios, one associated with the lower limit of 1.8 MeV and another with the higher limit of 7 MeV. And what you see on the plots are that all of the cosmological constraints, except for the top right contours, the black and the yellow, it's allowed. So any signal that happens below these two upper contours could be explained by this model. The diagonal reddish and bluish lines that you see are the cases when the decay happens at the temperature of the matter radiation equality, and they match different values of N effective. So the decay that we are talking about can happen anytime from when the mass of this sterile neutrino, the temperature of the universe is that of the mass of this sterile neutrino, or matter radiation equality. And for each, as I mentioned before, this 3.044 would be the value associated with the standard electron-positron enhancement, and assuming lambda CDM from the Planck 2018 datasets, and this 3.48 was the value that I showed that adding the H0 prior preferred. So this 3.48 would be an ineffective associated with a solution or an alleviation of the Hubble tension. So the main idea of this work is that low reheating temperature universes tighten up with new neutrino physics, can broaden up observationally consistent and novel cosmologies. This dark radiation can be a combination of thermal plus no thermal radiation, and can produce a novel cosmic microwave background signature that can be detected by upcoming laboratory experiments. And in addition to this, this model can provide this extra N effective that, as I showed before, can solve the H0 tension. So, well, these are the main conclusions. If anything's not clear, I'm happy to debate more in the live discussions, and I'm more than happy to take any questions you may have. Thanks so much for your attention.